G'day viewers, in this segment I'm going to introduce the physical layer. So here's where we are in the course. This figure shows a layered protocol diagram, and you can see out of all of the different layers we're going to start down the bottom with the physical layer, and then through the rest of the course we're going to work our way up to the application layer. Now, the physical layer is all about how we use signals to represent bits so that we can convey bits across a physical channel or a simple link from one end to the other. So you can see here, if we just consider a wire as an example of a physical layer, we've got here bits going in on the left, binary digits, that's the message we want to send, and bits coming out on the right. That's wonderful, that's what we wanted to get out, the same bits. But of course, if you were to look in the middle of the link here, if you were just to cut the link, you wouldn't see these bits anywhere. What's carried across a physical channel, like a wire or a wireless or fiber optic, is an analog signal. So we're going to need some way to represent digital bits with those analog signals. That's really the heart of the physical layer. So to understand how this whole process works, we're going to go through several topics. First of all, I'm just going to talk about the different kinds of media and their properties. So this is where we'll learn just a little bit about different kinds of wires, wireless medium, fiber optics, and so forth. Then I'll talk about how signals propagate over these different medium. This will introduce us to concepts such as bandwidth, attenuation of signals, and so forth. And equipped with all of this learning, then we'll build on top of that and really get to the heart of the physical layer, and that is how to represent bits using signals, the kinds of signals which will go over these physical channels. These schemes are sometimes called modulation schemes, how to encode bits. So this is what we'll look at. And finally, in the physical layer, we'll talk about some fundamental limits which constrain how well any real physical channel can do. And this will give you some sense of the bounds that are possible. So those are all of the topics we're going to cover. Now, by the time we've covered them, you'll understand how the physical layer works, and we'll also have we'll help to have realized a simple abstraction for a link or physical channel. And that abstraction actually is all that the higher layers are going to need most of the time when they use links. That's really following our layered protocol model. We're learning about the internals inside a layer, but the layer is going to expose an abstraction to the higher layers, in this case the link layer and beyond, to use. So this simple model is really all, in some sense, that the higher layers need to know about links. And here is some of the key bits of that model written down here. So I have, here's my simple link, or physical channel. This is a wire. I'm sending the message across it. You can see it's going over here. And there are just a couple of key parameters here. There is the rate, that's R. The rate might sometimes be called by different names, the bandwidth, the capacity, the speed. It's really the rate in bits per second at which a message can be sent onto this channel. And the other parameter is the delay. It's the delay D in seconds. And that delay is the amount of time it takes for the signal to cross the physical channel. So it's related to the length of the signal. Now, there are other properties of physical channels that are important and will sometimes rear their head and we should understand. One good example is whether a channel is broadcast. Wireless links tend to be broadcast, for instance. On a broadcast channel, when a message is sent by a receiver, it is received simultaneously by when a message is sent by a sender, it is received simultaneously by all receivers that are within range of that sender. Other kinds of media, like wires, for instance, are typically not broadcast. They just go from one sender to one receiver. And we may also sometimes care about whether a link has a very high or a very low error rate. Media such as fiber have very low error rates, so when you send a message across it, if it's engineered well, nearly all of the time you'll get the message intact at the other side. Other kinds of media such as wireless channels have high error rates, so wireless messages will quite often be garbled. And we're going to have to, of course, eventually we'll get to mechanisms to deal with that and fix that, so you're not going to send bogus bits onwards. Well, actually, given that simple model, we can already start to do some useful things. So for instance, we can already compute the message latency, and that is really the latency or the delay to send a message across a link. Let's think about what this delay is. Now, it actually turns out that it's really composed of two different components, two separate components. First of all, there's something that we call the transmission delay here. And this is really the time to put this message, made that's m bits long, onto the link, sending it out at a certain rate. So that delay, that component is really m divided by r. That's all it is. The second component is what's called the propagation delay. Once bits get onto the wire, they have to go from the beginning, where they just entered the wire, to the other side. Now, it takes a finite amount of time for signals to propagate down the wire that's related to the length. In fact, the propagation delay is given by the length divided by the speed at which signals propagate in the media. And for most wires and fiber optic media, 2/3 of the speed of light is a good example. For wireless, maybe the speed of light, close to the speed of light, is a better example. But basically, it's the light divided by the speed at which signals propagate in that medium. And we'll refer to that as Ds, because we'll often be given the delay in seconds rather than as a length measurement in feet. So if we combine these two things, we have that the latency to send a message over a link is m divided by r plus d. Well, let's see a little bit of an example of that. Oh, sorry, before we have an example, this is just a cleaned up slide with a little more detail that you can go over in your own time. Well, before we go over an example, I'll briefly just talk about some of the metric units that we'll use here and elsewhere in the course. You can see this table just lists some of the common prefixes. We'll use kilo, mega and giga for 1,000, million and billion, and milli, micro and nano for thousandth, millionth and billionth. These are all standard terminologies, standard notation rather. And in addition, we'll generally stick with powers of 10 to describe rates. So that means that 1 megabit per second will be a billion bits per second. But we'll occasionally use powers of 2 when we're talking about quantities of only storage. So for instance, 1 kilobyte a second is going to be 2 to the 10, or that's 1,024 bytes. This is just sort of following standard practice. Storage quantities are often expressed as powers of 2, whereas rates tend to be powers of 10. And you'll also see we'll tend to use a capital B for bytes and a lowercase b for bits. Okay, so on with a couple of examples. Well, I've got two different cases for us to compute the message latency. First of all, here, let's consider dial-up sending over a telephone modem. This is an old style use of sending bits of information over the telephone network. So the rate there was 56 kilobits per second is a fast modem, 56,000 bits per second. And we'll just talk about a delay of 5 milliseconds. So that's we're sending from your computer to another computer fairly close by, maybe in the same city. So what's the latency going to be? It's going to be equal to m divided by r plus d. Well, first of all, I'll do the plus d because that's easy. We've got 5 milliseconds plus m divided by r. I've got 1250 bytes. I'm going to multiply by 8 to get that to bits, and I'm going to divide by 56 times 10 to the 3 bits per second. And what's that equal to? Well, if you do the math, you should find that it's equal to about 184 milliseconds. Wow, well that's kind of interesting. And it's interesting because the delay here is not a dominant term. In fact, it's this last part here which contributes greatly to the message latency. That's where nearly all of the latency is coming from. So simply the time to get a message on a wire can be a key factor in the latency. Let's see another example, a different scenario. Now I'm talking about sending information across the country, and you've got broadband access via cable or DSL at home. So let's say across country, we'll call that 50 milliseconds. And the rate, you've got 10 megabits per second is what you've got from your provider. So let's compute our latency again. So I've got 50 milliseconds plus m divided by r. So that's 1250 times 8 divided by 10 times 10 to the 6 bits per second. Well, that's 50 plus, this is 10 to the 4 divided by 10 to the 7. That's going to be 10 to the minus 3, which is actually a millisecond. So this is 51 milliseconds. Okay, well, interesting. So in this example, nearly all of the delay is coming from the propagation delay to send the message across the country. The transmission delay component is almost nothing because we have a reasonable speed. So here you can see I've just cleaned this up a little more, and the point that I want you to take away is that either a long link or a very slow link, both of these can contribute to the latency of sending messages across the link. Now, and also often in practice, one of the delay components is going to dominate. So if we have reasonable rates, we'll generally tend to worry more about the propagation delay. For instance, if we're talking about sending messages across the country at a reasonable rate, you won't even need to compute the transmission delay because it'll be too small to add significantly to the message latency. Okay, well, so we've done message latency. Great. This model turned out to be kind of useful. But wait, there's more. I'd now like to tell you about something called the bandwidth delay product. It is a kind of an interesting realization to think that messages actually take up space on the wire. So it's as if some messages, a volume of bits, is actually stored inside a wire when you're using it to send a message. You've sent it from the receiver, yet they haven't reached the receiver. This quantity, the amount of data in flight, is called the bandwidth delay product. And the formula for computing it is this. It's to simply take the rate at which you're sending bits into the wire or other media and multiply it by d, the propagation delay before those bits get to the other side. That gives us the volume. You might measure this in bits or in other units for convenience, like in terms of fractions of messages or packets, just depending how you set the units for your calculation. And what you should find is that the bandwidth delay product will be very small for things like local area networks, where we're like a Wi-Fi, but it can be large if we're talking about networks where both the rate is high and the delay is high. These are sometimes called long fat pipes. Imagine a gigabit per second link which goes across country, for instance. Well, let's do an example to get the hang of it. Here we're going to look at sending data across Australia, it looks like from Perth to Sydney. So I'll assume here that the rate is 40 megabits per second. So you've got a good maybe fiber connection from your ISP and you're at home. And the delay for signals to propagate across the network, across that link, is 50 milliseconds for across country. So let's see, the bandwidth delay product now is equal to 40 times 10 to the 6 times 50 milliseconds. So that's 50 times 10 to the minus 3. Putting that together, we have 2000 times 10 to the minus, 10 to the 3. And that's in bits, so if I convert that to bytes, we'll have 250 kilobytes, the 10 to the 3 being a kilo. So 250 kilobytes. Wow, well, here's just a cleaned up version of that. The point I want you to take away is that that's actually quite a lot of data that happens to be stored inside the network. Oh, pretty good picture. Actually, it's like a small novel if you just consider all of the text. And all of that is just hanging out in the network. Okay, so now we put our model to use and you have some introduction to the physical layer. We'll go into the physical layer topics in the subsequent lectures.